Right, hi there guys. I'm just going to do a bit of a revision with you. I think some of you are feeling a bit apprehensive about the waves. So I'm going to go through the important stuff that I want you to know. The rest of the stuff, like the sound waves and that, I'm not going to test you on it, okay? So this is basically the stuff that I want you to know, because this will come up again in matric. Okay, so we're looking at transverse waves. Now I found this quite a nice diagram to show you what's going on, just to help you think about this. So I did speak to you about how it works very similar to a Mexican wave that people do at sports events. But here you can see exactly what I'm meaning. So this person's like squatting and then standing, and then almost you can think of it as tippy toes with hands up in the air and then come back down. So you can imagine, you can see now how the wave is now going from there to there, and it's moving across there, and how these people are just going up and down. So the wave will move across, the disturbance of the people will move this way, but the crowd or the people just go up and down. And that is what we mean by the particle motion is perpendicular to the wave motion. So if you could imagine their heads as a particle, the particles just going up and down, but because the next one will start going up or next one start going down or whatever, that will then show the direction. So you can see this one had already been with his hands up, and he was now starting to go down. Then this one has his hands up. His next move is going back down. This one is on his way up to put his hands up, and so that's what the wave will look like. So over here, what I've done is I want you to imagine the heads as if they were particles. Okay, you could use the hands, I suppose, but the heads, you can relate that to particles, I suppose. Okay, now if we have a look at that, all I've done is I've connected the dots, and you can see here, there and there, to the highest point of a head and to the lowest point of the wave. I'm hoping it's going to be very similar. Okay, this is not scientific, but I want you to see that this is the amplitude. Okay, where they are just standing, normally that would be their rest position, because they're just standing. Here they're starting to bend down and squat, and then here they're starting to raise their hands and then be on their tippy toes, and look how they bending their knees. Okay, so I want you to imagine where the line is where the rest position is, where they're just going to stand. And so if the wave is going in that direction, you can see these ones are squatting, and now they're going to be doing what this one's doing, and then this one and this one. So this one's already standing, which means it's going to be coming back down. This one's going up, up. This one's going up, gonna go up, gonna go up, gonna go up, gonna go up, and so it goes along like that. I hope that helps you to visualize the transverse wave. So let's just go through amplitude. It's the maximum distance from the equilibrium position. It doesn't matter if it's going from the equilibrium position down to a trough or equilibrium up to a crest. It's the same distance. Wavelength, distance between 2 points that are in phase. So this man standing with his hands up and that man standing with his hands up. The distance between those two men would be the wavelength. Be careful. This person here with his hands slightly raised and that person here raised slightly is not in phase. Let's just take a look over here. You can see that this person is going up and this person is going down. Even though they look the same, in the same position, they are moving in opposite directions, so they can't be in phase. So the same with this one, and this one. This guy's going to start moving up, and this guy's going to start moving down. So you need somebody that looks like this guy, but is also starting to move down, and there he is there. Okay, so there to there would be a wavelength. Okay, and the wavelength is the same all the time. Frequency, the number of complete waves that pass a point in a second. So if we had to time it, and let's say we, as soon as this guy's got his hands up and we push the timer, when he does that again, where his hands go up and we stop the timer, oh sorry, that's period I'm thinking of. What we can do is we can watch this guy, And in 1 second, we can see, did he go from, maybe he went from that position to that position, or that position down, and either half a wave went past, or a full wave. Maybe in 1 second he went down and up again, and that is what a frequency is. How many waves pass you in a second? Now the period now is if you take the time of him going from his highest position down, down, down to lowest, up, 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 back to his high position. And that would be the time taken for one wave to pass. Okay, these are inverses of each other, the frequency and the period. All right, so the equations I want you to know how to work with. This is velocity is equal to wavelength over time. Now this really focuses on other waves. So like any other transverse wave, or even longitudinal waves like sound, you can use that. And then obviously you can change it up based on this. So frequency is 1 over period and period is 1 over frequency. And so they can interchange like that, the period and the frequency. This is the EMR equation. So this is electromagnetic radiation specifically. So remember, this is your radio waves, your microwaves, your, what's next? Infrared, then your red, Roy G. Biv, rainbow, then your ultraviolet, your X-ray, and your gamma. Okay, so it's all of those waves. Okay, and these are the ones you can use. Notice how the velocity or the wave equation changes to a C, because all of these electromagnetic waves travel at 3 × 10⁸ meters per second. So already we have this speed. And then we use Planck's constant to find out the energy that each photon in these carry. Okay, the amount of energy that they carry, and it is based on their frequency. The higher the frequency, the higher the energy. Notice the relationship. They're on the same level, which means direct proportion. Here, the energy and the wavelength are not on the same level, so these are indirect. Okay, 1 over wavelength. It's an indirect relationship. The bigger the wavelength, the smaller the energy, because it's the same relationship with frequency. Okay, so I'm going to do some examples with you, and then I want you to try some examples on your own, and then we'll be done with waves. Please let me know if you're still not, any of you are not getting this. I will try and do some more examples and maybe send you a video privately. Okay, so the diagram represents a wave with a frequency of 20 hertz. Okay, so what does that mean? It means that 20 waves pass a point in 1 second. That's what it means. Oh gosh, can't spell. Okay, 20 waves pass a point in 1 second. Okay, so we're looking at this and we see the motion is going over there, and we are basically tracking what the particles are doing, and we can see what's happening there. So what is the period of the wave? Okay, so the period of the wave, we have the frequency. Okay, and now we know from above that the frequency, oh sorry, let's start with period. Period is equal to 1 over frequency. Oh crap, I've lost my calculator's not here. And so it will be 1 over 20. Okay, and that's in seconds. So we've got 1 over 20. Oh, what's that? Oh, I can't think. I'm quickly going to get my calculator. It's just here. Sorry. Okay, so all you have to do is 1 divided by 20, and you get 0,05 seconds. Okay, so there is that. All right, so what is the wavelength of the wave? Now, it shows all of that as being 10 meters, but let's just see how many waves there are. So we're going 1. Remember, it's back to its original position. 2, 3. So there are 3 waves. So if we say 10 divided by 3, it gives us, oh, sorry, I haven't done that one. Okay, I'll go back to 2 now. 3,33 meters because there were 3 waves in 10 meters. Okay, how long does it take for 3 waves to pass point C? So remember, period is the time it takes for 1 wave. So to get 3 waves, 0,035 times 3, and that will give you 0,15 seconds, because it's that times 3. Okay, because remember, period is the time for 1 wave. What is the amplitude of the wave? Again, this one gave you a measurement from the peak to a trough, but we know that it is actually from there to there, and we can halve it because these values are equal. So it would be 1 meter, 1 meter. So the amplitude is 1 meter. In which direction is point B moving? Okay, so here's point B. Now, if the wave is moving that direction, that means point B was at the top now, but it has now moved over to the side. So this one is, B is actually moving down. Okay, it's now heading to go to the trough, or become a trough, if I could say that. Okay, so down. Calculate the speed of the wave. Okay, so let's just see what we have here. We've got wavelength, and we've got frequency. So we can use this one. You didn't know what type of wave this was, so you can't use your EMR because I didn't say what it was. If you can't, and you can't just assume that it is an EMR. Okay, frequency times wavelength. The frequency is 20 hertz from the above question here, times the wavelength, which is 3,33 meters. Now, girls, what I would do for you is that if you okay, 66,6 meters per second. So if you get the wavelength wrong here, I will carry your mistake over here. So let's say you made this 4, and then you put 4 here, and you went 20 times 4. You will get all of those marks if you did this all correctly over here. Okay, you'll just lose the marks over there. All right, so let's take a look at some of the other type of questions. This is using your electromagnetic radiation. I can't remember where I got these questions from now. I don't know if I got them from a past paper. In an experiment, a researcher uses microwave and X-ray photons with very different energies. The frequency of the X-ray photons is measured as that. So let's just go photons. And always, girls, write it down. Write down what you've been given so you can see what to work with. Okay, there's my frequency for photons. And the microwaves are 4,5 times 10 to the 10 hertz. And that is my frequency then. Okay, calculate the energies of the microwaves. Compare the energies of the microwaves and the X-rays used in this experiment. So energies, that means that we're probably going to need Planck's constant over here. Okay, so we have the frequency, so we can very easily use, and I'm going to put this equation here in the middle so I don't have to write it twice, and there it is there. So the first one we're going to do is equal to 6,6 times 10 to the minus 34. Remember, this is it's a constant, will be on your data sheet, and you must just know to use it, times the frequency 3 times 10 to the 17. Okay, please, girls, if you're battling with scientific notation, I'm going to show you how to use this button quickly, because I know even the matrics were struggling and I had to teach them how to use the button. Okay, so you have to go 6.6, then this button down here, you just push it once, okay, and it shows you 6,6 times 10. Now it's waiting for you to put the exponent in. You don't have to now find the exponent. It has the exponent there already. So even though it looks big, it is not. Now you've entered it properly. Then you can go times 3 button times 10 to the 17. I don't have to go anywhere else, okay. And then I get the answer of 1,98 times 10 to the minus 16. You need to get your eye in for scientific notation, please, girls. And this is energy, so it is joules. Okay, so let's take a look at the next one. So we're going to use that equation again, and we're going to go 6,6 times 10 to the minus 34 times 4,5 times 10 to the 10. Okay, and again 6.6 times 10 to the minus 34 times 4.5 times 10 to the 10. And we get 2,97 times 10 to the minus 23 joules. So if we have a look here, now be very, very careful. This 1.9 is smaller than 2.9, but take a look at those exponents. This one is, this whole thing here is actually bigger because it is, the exponent is minus 16, where this one is minus 23. So when you go 0,00000016, you're going 16 times, and here you're going 0,00029, you'll go 23 times. Okay, so this one is actually bigger. Okay, so the energy of, oh, I put the wrong value here, sorry, it's supposed to be X-ray photons. Okay, the energy of X-rays is greater than microwaves. Okay, so because girls, remember, you've got to answer the question, compare the energies. Doesn't mean now you've just left it there. You have to say, oh, okay, well, I see this one is bigger or smaller. Okay, answer the question. Right, Neil Armstrong was the first person to walk on the moon. The distance between the Earth and the moon is so many meters. Okay, calculate the time it took for his voice to reach the Earth from the moon via radio waves. So we are using radio waves. Okay, so we know that the speed of his voice traveling along with radio waves is that. Okay, we have a distance. Okay, so we can use a speed, distance, time formula here. Okay, speed is equal to distance over time. I'm sure you've done this in maths. Okay, and it's basically the same as the wave equation. And so we've got the distance of 3,85 times 10 to the 8 over the time, which is what we are looking for, and the speed is 3 times 10 to the 8. So to get that, remember, you times to get it away from this side, and then it would be 3 times 10 to the 8t, and then you're going to divide by 3,8. So you're basically swapping those two around. So that means t is equal to 3.85 times 10 to the 8 divided by 3 times 10 to the 8. Okay, and it would be 1,28 seconds. And that's how long it took to get to the Earth. Okay, photons in an electromagnetic wave have energies of that. Calculate the frequency in megahertz. Okay, so let's calculate the frequency first in hertz, and let's see what we can do. So we have the energy. Write down what you've been given, because that really does help. Times 10 to the minus 26. Okay, we want the frequency. So what can we use? We can use this equation again, HF, and we now have, because you know you're using a lot of maths and science now, hey? Minus 26, 6,6 times 10 to the minus 34, and there is my F. So you just substitute it as you normally would, and then solve for the equation. So that will then go under there, and you'll have that divided by 6,6. So 1,989 times 10 to the minus 26. Oh, yes, that's right. Divided by 6,6, it's minus 34. Okay, now you can see the value. It's quite long. So we want it in megahertz. So it's 30,136,363,64 hertz. Okay, so now they said into megahertz. So we're going to move this by 6, because mega means a million. 1, 2, 3, 4, 5, 6. So it's 30,14, 2 decimal places, megahertz. And there is our megahertz. Okay, last one, and then I want you to try on your own. The photons in an electromagnetic field, electromagnetic wave, have so much energy. Calculate the wavelength. Okay, so now we have this energy. Okay, so many joules in the photons of an electromagnetic wave. What is the wavelength? We are looking for that, which means that we can then use this equation. Now, there's 2 ways you can do this. You can use this equation, or you can use the one with frequency and then use the C is equal to F lambda to get the wavelength there. But it's just so much easier to use one equation. So that would be 1,57 times 10 to the minus 20 as our energy. Then we have 6,6 times 10 to the minus 34 times the speed of light, or the speed of electromagnetic waves, divided by wavelength. Okay, so again, we swap those 2 around, and our wavelength is, so there, I hope you can see that. Okay, so it would be 6.6 button minus 34 times 3 button 8 equals, divided by 1.57 button minus 20 equals. Okay, and we get 1,26 times 10 to the minus 5. You normally round off to 2 decimal places unless it was stated otherwise. Okay, so make sure you've got that. Okay, so that's what I'm going to be doing with you today. The rest of the worksheet, you'll see there's an exercise for you. I want you to try it. Today's the last day of waves. Tomorrow we're going to start with quantitative aspects of chemistry. So we're doing some more maths with chemistry. And the answers are after your exercise. So you can check how you're doing, okay? What I did was I took it from a past paper. So try and do that one now quickly and see how you go. And then tomorrow we'll start with a new section. We'll go to chemistry. All right, have a good day.